Okay, our professor gave us some practice problems from the inventory, and so that's what I'm going to go over. It's number 4 and number 27. So a large law firm uses an average of 40 boxes of copier paper a day. The firm operates 260 days a year. Storage and handling costs for the paper are $30 a year per box, and it costs approximately $60 to order and receive a shipment of paper. What order size would minimize the sum of annual ordering and carrying costs? So first step is we have to look at our given parameters. Our average daily demand is given. We know that is 40 boxes a day. But now we want to find our annual demand. Well, this is important, and that's why they gave us that 260 days a year, because it's 260 days a year times their daily, and that's going to give us 10,400 for our annual demand. I'm going to erase this just so everything is simply put, but I did want to show how we got that. And then we have our annual holding cost, which is going to be H, and that's going to be $30 a box, or yeah, $30 a year per box, sorry. And then our ordering cost, which it says it's approximately $60 to order and receive, so that means S is going to be $60. Now we need to see what order size would minimize the sum of that cost, and that means we're going to use our EOQ formula. That is going to be Q equals the square root of 2 times D, you don't need the parentheses, sorry, S all over H. So for this, we can go ahead and just plug everything in and solve. It's the square root of 2. We found this 10,400. Also, all times S, all over H. So then we can go ahead and plug that in, and this is going to give us just about 41,000 the square, and then when we find the square root, it is 203.96. This is the optimal ordering size. I'm saying that because it will come up later, but in this case we are going to be rounding to 204 boxes because obviously we cannot have 0.96 of a box. Now I'm going to leave up our given parameters as we move on to the next question. And this next one is asking us to compute the total annual holding cost using your order size from part A. So we just found part A is 204. I'll put that here too. So this means, like I just said, Q is 204. We need to find the annual holding cost and the annual ordering cost. So total cost is going to be annual holding cost, which is Q over 2 times H, plus our annual ordering cost, which is D divided by Q times S. So if we go ahead and just plug these things in, 204 over 2 times 30 plus 10,400 all over 204 times 60. I'm going to go ahead and start it smaller off. So this is going to be 102 times 30, and then this one is going to be 50.98 times 60, and then over here this is going to give us 3,060, and then over here it's going to be 3,058.82. If we add those together, I don't have room, so I'll just do it big in red. If we add those together, that means our total ordering cost is 6,118.82 cents. So our next question is asking us, except for rounding, are annual ordering and carrying costs always equal at the EOQ? And the answer is going to be yes. We want to find the absolute minimum. In our PowerPoint, it goes through and explains how the total cost curve is a U-shaped, and it's going to reach the minimum exactly at the point where the carrying costs and the ordering costs are equal. The EOQ formula, what we just did earlier, is designed to find where both are perfectly balanced. And the reason it's saying except for rounding is because when they're not rounded, when it's at 203.96 we found earlier, they would be equal. We found when we were finding total costs, 3,060 and 3,058.82, they're slightly different because we rounded it. If they weren't rounded, they would have been exactly equal. So that's what that one means. And then if we go on to the last one, the office manager is using an order size of 200 boxes. The partners of the firm expect the office to be managed in a cost-effective manner. So would you recommend that the office manager use the optimal order size instead of 200 boxes? So justify your answer. Yes, so the optimal size is going to give us the lower price. If we want to justify it though, we can go ahead and plug in 200 boxes into our total cost formula. And so that's going to give us 200 instead for Q. 200 over 2 times 30 plus 10,400 all over 200 times 60. So that's going to give us 3,000 plus 3,000 plus 3,130. And if we add that, that would give us 6,120. Well, it's not that much more. It is more expensive than the optimal price we found of 6,118.82. So that's why it would be better to increase it to 204 boxes for the optimal lowest price. And then our next question is saying Ned's Natural Food sells unshelled peanuts by the pound. Historically, Ned has observed that daily demand is normally distributed with a mean of 80 pounds and a standard deviation of 10 pounds. Lead time also appears normally distributed with a mean of 8 days and a standard deviation of 1 day. What ROP would provide a stock at risk of 10% during lead time? So first off, we need to find our given parameters. Our mean daily demand, oops, that looks awful. Oops. Okay, so our mean daily demand is going to be, oh my gosh, what am I doing? Sorry, okay, is going to be 80 pounds. Why won't it let me write? There we go. Is 80 pounds. Our standard deviation is going to be 10 pounds a day. Our mean lead time is going to be 8 days. And then our standard deviation of our lead time is 1 day. And our stock at risk is given, it is 10% for our stock at risk. So first we need to determine the service level and the Z-score. Our service level is 100% minus stock out risk. So that would be 100% minus 10% that we were given, and that means it's 90%. For our service level. So on a normal distribution, that means our Z-score is going to be 1.28. So now we need to find which case it would be. In this case, both of them have a variation. That's why we have a mean for each of them. There's a standard deviation and a mean for each of them. So our formula, I'm going to erase this just so we have as much room for this. Our formula for ROP is going to be the mean daily demand times our mean lead time plus Z times the square root of the lead time times our standard deviation, our standard deviation of daily demand squared plus our daily demand mean, squared. I don't know why this is getting, the pen's being weird. And then that's all times the standard deviation lead time squared. This looks like a lot, but all we need to do is plug things in. We have all of these numbers. I'm going to do this piece first, and then I'll do this piece after. So this piece is just 80 times 8. That's going to give us 640. I'm going to leave that there and go ahead and erase this stuff for some extra room. So now we can do this other part, and I'm going to put our Z is 1.28. We just found that, so 1.28. And then in the square root, we are going to have the mean of our lead time, which is 8. And that is going to be times the, I have my notes that I'm reading off of right now. And that is times the standard deviation of daily demand squared, which is going to be 10. And that is plus our daily demand squared, which is 80, times our standard deviation of lead time squared. So this is going to give us 8 times 100, which is 800, plus this is going to give us 6,400 times 1. So in our square root, we are going to have just about 72,000. Once we solve for that, that is going to give us 84.85. We multiply this times 1.28, and that is going to give us 108.61. We add these guys together, and that is going to give us our ROP of 748.61, and we are going to round this as well to 749 to have the nearest full pound.